So hello everyone, and for those of you who don't know me, my name is Mary McGeoch. I'm a director of the Asset Plan. It's my own consulting firm since 2010. So a bit about me, I have a PhD in strategic engineering and infrastructure asset management. I co-developed an asset management maturity and capability model. I also have a background in organizational psychology and development. So I work with organizations currently as what I call a human bridge to link human capability with technology and with asset management change and operating model implementation. So today I'm going to be discussing a problem that really sits at the intersection of two things that many organizations are tending to treat separately. And the first is old and new or emerging technology, and the other is asset integrity led by asset criticality. So my proposition today is simply that technology should be embedded within asset management as an integrity discipline anchor, and asset integrity practice is transformed when you embed the right technologies properly. So in order to discuss this, I'm drawing on my current research, which is existing examples from mining, heavy industry, including a blend of external research combined with some of my own operational experience of 26 years. Now, a caveat for this is that it's quite a dense subject and it's only becoming broader. So I'll cover what I can in the time that we have and arrange for Heather to have the slides and sources available afterwards. So if we just go on to slide 2 for me, Heather, thank you. Okay, so today's session really centres on understanding and closing the gap between integrity, insight and action as mining companies continue to embed rapidly emerging technologies. And we see these evolving, and I use that term rapidly emerging quite deliberately. So the critical link that I make in this context is to integrity practice. It's foreseeable failures identified, prioritised and acted upon. And today I'm going to aim to achieve this linkage in 4 ways. So the first is why technology pilots typically don't reach sustained operational use. Number 2 is methods used to link risk with asset criticality in order to support prioritization. 3, what a defensible, i.e. a legal, regulatory compliance, assurance, inspection regime looks like at a high level. And 4, why operational readiness is what makes integrity decisions survive what we're all very familiar with in mining is that downturn. Cost pressure. So just regarding scope, and Andrew, I heard you talk about a safety share earlier, and I really get into quite a catastrophic safety share here in tailings. And my examples tend to lean heavily on this, and it's deliberate because it's one of the highest consequence asset classes we have. It's one of the very few where the precursor signal is genuinely measurable weeks out. It has a global standard and published data showing that the implementation can still lag. So the disciplines I talk about are applicable in varying forms to other critical mining assets, haulage, processing, remote operations, and some other examples as I go along. But in the future, and maybe this is for discussion as a working group, we can visit other critical assets in future sessions. So if we just go on to slide 3. Now for this slide, I want to talk about an incident from March 2026, so this year. So Santa Fe, Sinaloa, 25th of March, a tailings pool directly sited above one of the mine's access tunnels gave way to 175,000 cubic metres of sludge into the workings. So 25 men are underground, 21 got out, 4 were trapped, 2 were rescued. Francisco Najera spent more than 300 hours. Unfortunately, 2 other individuals were killed from what I read. And this catastrophic failure didn't come from the extraction process that was being undertaken at the time. It actually came from the built engineering systems. The tailings dam sited directly above a tunnel. So the signs of failure in this case and cases like it tend to be slow degradation but instant release. So the signs that I've listed on the slide here develop over weeks and months. The actual release itself, and you'd be familiar with this having seen events, it happens instantly, takes mere minutes and is catastrophic in its result. So at that time, people are scrambling and they usually can't intervene as effectively during the event for obvious reasons. So the endeavour is to prepare before it. And the first image I have here is responders at Santa Fe using a 3D model of the mine during the crisis in order to rescue the trapped miners. Now, there's been other instances that I've listed on the slide, but I also want to highlight Brumadinho a catastrophic failure in 2019 of a tailings dam at an iron ore mine complex, storing roughly 2 million cubic meters of tailings. 3/4 of that was released downstream. They reportedly monitored using geotechnical techniques, but the collapse happened without any apparent warning, and it claimed 272 lives. Significant environmental damage was caused. That is catastrophic. So I looked into why monitoring didn't help. I reviewed an expert panel's retrospective summary, and the dam was actually extensively monitored using a combination of techniques. So surveying monuments along the crest, inclemented deformation monitoring, ground-based radar, surface deformation, piezometers to measure the change in internal water levels. And that's just a few of the instruments that I found. So none of these detected any significant deformations or changes prior to failure. So I was interested as to why that was. And some of the insights I got from the panel and some retrospective research showed that the technology to see this actually does exist. So the second image I've got at the bottom is an InSight image, and Greby et al. Looked at retrospective advanced analysis using this imagery. They found that satellite data had these failure indicators 44 to 51 days out, and at the earliest starting to show at 75 days. Lombroso actually looked at an agent-based life safety model to scenario test a dam breach mud flow model. So a simulation, not a real scenario, on 502 people at risk. They modeled simulated fatality numbers ranging from 456, where there's no warning, to 0 fatalities with 15 minutes warning. So their conclusion is that emergency planning for tailings dams can be materially improved process-wise. Now, as a result of these failures, the GISTM was written. It requires monitoring across the whole facility life cycle, but it's voluntary. So it doesn't displace laws and it doesn't bind anybody. At this point in time, well, as at November 2025, it only has a third of global members partially conformant. So based on all of this, our goal is to capitalize on technological capability before the failure, not during. Now, if we just go to the next slide. Okay, so in looking at this topic, slide 4, I just wanted to cover technology deployment. It's been in practice for decades. The argument it isn't mature yet is not really the explanation for why pilots are unsuccessful. So it's not the technology is what you'll hear me say today. Of the 6 examples, only Vale is tailings. It's one example of a critical asset that I'm threading through this argument to highlight the position, but it's not the entire scope of the research. I'm restating public record of what I've found, good, bad, and ugly, not endorsing company, vendor, operator. I'll speak from left to right, then top to bottom, but I won't read the slides verbatim, just for the sake of time. But examples here, we've got Rio Tinto, so autonomous haulage in the Pilbara, no attributed fatalities since the 2008 trial. The capability, though, is limited just due to being Australia concentrated, and replacing in other jurisdictions has been slower. BHP Digital Twin and GenAI Pick to Port. BHP's self-reported predictive maintenance on crushers and conveyors and value chain digital twin credited as part of a 65% reduction in fatal potential events across iron ore in WA. The bad/ugly is that in Jimblebar, there were 2 autonomous trucks that collided due to wet ground. So it's still net safety positive, and BHP self-reports it. There are 75% fewer collision incidents at Jimblebar than at its non-autonomous mines. Third box is Vale, and I've highlighted this as sort of the bookend to Santa Fe on the previous slide. It's the ugly first is why it exists, because of the events after the catastrophe that I described earlier. Vale built these geotechnical monitoring centres, watching the dams continuously with remote operations into high-risk areas, so nobody is exposed during tailings removal. Now, the bottom row, Newmont, technical deployment here is complete, but full operational commissioning is still in progress, partly due to planned employee changes. In Sandvik and Barrick, remote monitoring service technology integration was actually disrupted after state takeover, then placed back in production. So not a technology failure, it was a political issue. XM Pro predictive maintenance vendor reported downtime reduction on targeted failure modes on conveyors. So I've written not all equal. So from my findings, there's varying evidence to demonstrate successful technological integration. And you can see here there's varying reports, self-reported versus demonstrated by the research. Not without incidents. Jimble was a good illustration of risk shifting to new failure mode. So automation doesn't remove risk, it just changes the shape of the risk. So we'll move into this in the disciplines later on. Other examples that I covered, Anglo America, Siemens, Commerce Digital Twins in Peru, and Fortescue I'll cover a bit later, but autonomous CAT integration at Cloudbreak in 2019. So we'll get that back into that in a little while. So the 90% figure that I've quoted here is from a survey, Mining Magazine and Australia's Monthly Mining, published by Bentley in 2025. When interviewing senior mining operation leaders, 90% reported near universal adoption, but not most of them, i.e. 90% not returning anything measurable, unfortunately. And we've got some other research to cite that later on. So what I found is that it isn't that technology didn't work. There are incidents and new failure modes arising when it goes in without a specific methodology or operating model. So I'll continue on to that now. And I'll just go on to slide 5, please, Heather. And just let me know how I'm doing for time, but okay. So on the left-hand side of this slide is a taxonomy of 4 failure modes. It's not a fair list of pilots, but the key gaps between insight and action. So for example, only one of these was a pilot, which was Newmont, and Brumadinho was actually a fully operational facility with a certified monitoring system in at the time. Number 1, poor data foundations. I don't think anyone here is going to be shocked by that. That's my own diagnosis, 26 years across mining and heavy industry, and it's almost always where it starts. And I have research to back it up, but I'm sure I'm not alone here. Number 2, no integration with decisions. So I covered this with the catastrophe on slides 3 and 4. The failure mode doesn't stop when you move from pilot to production. It actually usually becomes more expensive. So in Brumadinho, as I said, it cost 272 lives and $7 billion in reparations, thereabouts. Technology without process. Again, the previous slide on Newmont, and I've actually got an image on the top there. So the technical deployment of the twin was complete, but the full operational commissioning is actually reportedly still in progress. The technology went in, but the operating model, the people and the process around it didn't go in. So therefore, it wasn't operational. Missing operational readiness. So McKinsey, I'm citing and paraphrasing McKinsey, operating centres, remote operating centres under-deliver when leaders don't set clear expectations of bottom-line impact or position the centre with a limited authority. So here, they're saying that the theme is change management. And again, it's not the technology. Now, I'm just going to address the diagram I have. 3 studies measuring measurable P&L return, reaching production, significant value created, reported that AI initiatives failed to demonstrate return on investment in companies, in mining companies. And again, they found that these initiatives failed on process and operating model, not on technology. And that's the whole point of this slide. So every one of the 4 causes or failure modes on the left is a non-technical piece. So if we go into slide 6, what I start to talk about here is the gap. And the gap is what asset integrity practice closes. So start to explore what that looks like and how we achieve that. Okay, so this slide outlines what closes the gap between deployed technology and integrity based on the catastrophes, slide 3, real deployment, slide 4, and the failure modes on slide 5. So we've talked about poor data foundations. It's a first failure mode, and for me, it's a precondition. Without the data, nothing works. It's a DNA. Then I've applied 3 disciplines. It's my own working definitions. So where do we deploy technology? Base it on criticality and risk. It needs to drive it. Effort should follow consequence of failure, not cost, not ease of deployment, not what the vendor decides or has a demo ready for. So I covered this a bit more in slides 7 and 8. What the data must produce, it has to be a defensible decision. It has to be a record that would survive scrutiny by a regulator, insurer, auditor. I cover this in slide 9. And who is accountable? I talk about named decision rights. So the authority is given. It's in a position description. It's official within the business. A workflow changes and people then trust the output because it's visible, it's tangible to them, and it's consistent. So I cover this further in slide 10. The sequence matters too. So if you look at the who before the where, you might build a governed process that points at the right people and the wrong assets. If you answer the where without the what, you might generate condition data that never actually eventuates into a work order. So the method is important and the sequence is critical as well. Now, I'm just going to move on to slide 7, and I want to talk a little bit about criticality. And I don't think the 5x5 will be new to many people on the call, but I'll talk about it anyway. So this slide covers the critical asset families, or some of the critical asset families, the 5x5 framework, functional safety is a must mention, and other guidelines. 4 asset families, and just looking at this example, what I'm positing is that consequence should drive criticality. So a haul truck is expensive and breaks often, and a production stall is recoverable as a medium consequence. A tailings facility, again, going back to the example of the catastrophes that I talked about, and it's highlighted here for effect, it rarely fails, but when it does, it's absolutely catastrophic. The people, regulatory, environment license to operate, it's devastating consequences, and therefore high consequence. But then you look at, and I demonstrate this in the red box, criticality equals consequence by likelihood. So a tailings failure is consequence 5, but it's rarer than the bottom band of any 5x5. So it scores a 1 times 5 equals 5. In the standard matrix, that would band as a medium. Just as a out of interest, it's the same as a routine recoverable fault. This varies depending on organization, but that's the general findings. If I look at the green panel, I mentioned the GISTM previously. This was a specific response to catastrophic tailings dam failures. It doesn't actually rescale likelihood access or reweight the multiplication. It removes likelihood from the decision altogether and classifies by consequence. But as I mentioned earlier, it's not mandatory. It doesn't replace law, and it's something that isn't yet taken up. It's a third partially combined is what I found. So it scales design criteria, monitoring and governance of that classification. Other standards worth mentioning, the Dam Safety Management Guideline under the ISO 9001 is often actually used by dam owners to guide the adequacy of systems, used for planning, checking and reviewing dam safety management program. And functional safety, it's how industry prove a protective function is trustworthy, and using GMG published guideline for autonomous systems and driving that as reference as well. But key standard is the IEC 61508 and the 61511. The required risk reduction, not necessarily a matrix score per se. The LOPA divides the unmitigated event frequency by the tolerable frequency, and the tolerable frequency set by consequence severity. So rarity doesn't actually shrink the requirement the way that it does in a 5x5, which is why the 5x5 shouldn't be used, in my view, for consequences of this magnitude. So the target moves down as the consequence gets worse. And the next slide, slide 8, is where I talk about criticality, becoming a way of deciding where the technology goes. So I'll just move to that. Okay. So slide 8 is the first of the 3 disciplines that I'm developing. It's probably the most important because criticality assessment is not new, and it probably won't be new to people on this call, but it's the linkages that I'm trying to make together with these elements. So what I'm advocating here is using criticality as a primary lens for technology investment. So if you've done a proper criticality assessment, the consequence of failure across safety, regulatory, LTO, environment, production, finance, reputation, the technology really should go where the consequences are higher rather than where it's easiest to deploy, or not where a vendor already has a solution, like I said before. An asset criticality assessment is the prerequisite. I've done a lot of these. I've been involved in a lot of these, many of them, and mature programs generally do the ACAs across all, but your RCMs and FMECAs and FMEAs are usually the top 20 to 30 max, because covering the entire base as critical becomes uneconomic. The analysis cost exceeds the value for non-critical assets, and then you haven't prioritized anything. So as mentioned, Bale concentrated their monitoring on highest consequence assets they own rather than spreading thinly across the fleet. And as I was thinking about this, a non-generic or a generic non-tailings version of this is vibration and temperature monitoring on the most critical crusher gearbox, feeding straight into shutdown planning. The example I've got in getting it wrong, and that's getting it right, sorry, that's Vale getting it right, and getting it wrong is a generic example. Again, I've seen this across multiple industries, blanket sensor deployment across hundreds of low criticality assets, and then an analytics team overwhelmed with alarms, false positives, or alarms that don't have any intended notification ownership. So the signals start to get lost. And when everyone is accountable, nobody's accountable. So I'm just going to move on to slide 9. So the second of these 3 disciplines is defensible, inspection and insurance. So defensible means, to me, and there's varying definitions, but I incorporate scrutiny from a regulator, an investigator, insurer after an incident, even from a board. Not that we have a regime that we think is okay and we've done this a certain way for many years and it's always worked, or we've followed this process. So it has to be something that would withstand scrutiny. If I was in a court, I always say this, it's legally defensible. If I was sitting in a court of law, could I defend this? And the methods that I link to this are evidence-based intervals. So shifting from time-based condition-based intervals, having logic that's documented and auditable. Condition data, investing monitoring, generic data, and assurance that survives scrutiny. So digital inspection records, automated scheduling with compliance tracking, and tamper-evident audit trails. So all of these, it's evidence basis. I'm just going to go on to slide 10, just conscious of time as well. Actually, sorry, Heather, before I do that, I might just go back on to slide 9 for a second. I just really want to make a note on slide 9 about getting it wrong. So Vale's dam had an inspection and monitoring regime, and there was actually a stability declaration that was issued before it failed in 2019. So engineers had found that the dam did not meet the required stability factor, and they had actually reported drainage problems, but the declaration was issued. So we had an instance of stability declaration issued, and then unfortunately the incident occurred in 2009 and criminal proceedings finished. So it really just demonstrates my point that things have to hold up in a court of law. So I'll move on to slide 10. And the third discipline, and unfortunately the one that seems to get underinvested in, or sometimes rushed or not done properly or given the due diligence that it needs, is operational readiness. So trust is a human element. For example, if I'm a planner with 20 years experience and an algorithm tells me that a bearing will fail, but I think, hang on, this is based on my experience and my gut feel, this is not right, I'm going to follow my gut. So it's ensuring that we build trust by involving frontline people, the people who know the assets and the people who are involved with the assets and have been for decades sometimes in the design, being transparent and demonstrating accuracy. So then that leads to decision rights. And I talked about this, it's about that ownership, authority, and accountability. So if the analytics or the notification or the alarm flags an issue, well, who does that go to? Who decides? Who has the authority to make the decision, and what level of delegation? Who can overrule it? So if that's not clear, if the decision chain isn't clear, then decisions don't get made. And the decision chain then is what I've got an example of here. So an example is an alert fires, a reliability engineer raises the work order, the superintendent might defer it, but only with a document of risk acceptance. The operations manager decides to take the asset offline. So there's a flow. Every alert needs a named owner and a defined next step, coupled with authority. And I'm just going to go on to slide 11 very briefly. And look, slide 11 is really just a stress test. So we've all seen the downturn, commodity prices fall, cost targets cascade, maintenance and inspection budgets are deferred or cut. And step 6 is red because failures sometimes arrive when you're trying to capitalize on the upswing, and we go around and around again. So it's cyclical. It's a mechanism that repeats, and most people in this room or this call have been around the block once or twice. So I talk about the durability action. So it's a bit of a stress for the three, the where, the what, and the who. So if we can link every integrity activity to criticality and risk, can we defer this inspection? What risk are we accepting? Who is signing off? Then it becomes a conscious trade-off with a name attached. So it's not just a number in a spreadsheet. The what, if we use the technology to reduce the cost of assurance, not only to add capability. So drone inspection instead of scaffolding and rope access is what I have here. So we can actually demonstrate that we're reducing a significant risks where there have been prior near misses or incidents. And the who is the probability of failure, consequence in dollars and safety term. Make it explicit, recorded risk acceptance, and this is a decision right. So what am I signing off on and what are the consequences? And again, if I'm, excuse me, if I'm sitting in that court of law, is that defensible per slide 9? So I'm just going to go to slide 12, which is putting it all together. And I would hope that this is a picture of what it looks like when it's working. So criticality is what drives investment, which I looked at in slide 8, the where. Data connects to the decisions, which is the what. Operation owns the technology. So the people are ready, that they trust the technology, they trust the data. Integrity survives the downturns, and the precondition, it's the data foundations are there as a precursor. And just slide 13, just to wrap up. So 4 things to take back. Pilots stall on organisation and process, or what I call operating model, not on technology. It starts with criticality, number 2. So make sure the criticality assessment is current and defensible before you invest in the technology that you're looking to enhance. Number 3, defensible means evidence-based and auditable, a court of law. 4, the readiness is what makes it hold. So we need that operating model, organizational readiness, change management. Don't leave it out. Make sure it's part of the process. And that's it. I'll finish up there, Heather and Andrew. Thank you.